My work with the Jurekfest focused on the relation between loop quantum gravity and the spin-foam models. And my today's talk will be about this. I'll present what I think are the main two results of our work. One is a relation between the EPRL spin-foam model and loop quantum gravity. Engle, Pereira, Rovelli, and Livine constructed a spin-foam model whose boundary structure is compatible with some loop quantum gravity states, and we generalize this model to all states. I think this is not enough. We need a proper derivation of a spin-foam model from loop quantum gravity. And in fact, we derived a spin-foam model from a model of loop quantum gravity coupled to massless scalar field. Let me start with introducing the main players, loop quantum gravity and spin-foam models. The states of loop quantum gravity are described in terms of spin networks. A spin network is a triple, gamma, rho, iota. Gamma is an oriented graph. This is one example of a graph. A simpler example is a loop connecting a node with itself. That's where the name loop quantum gravity comes from. The links of a spin networks are labeled with irreducible representations of a compact group. Typically, this is SU2 group, and the representations are labeled with spins. That's where the word spin network comes from. The nodes of the graph are labeled with tensors invariant under the action of the group. An example is Clebsch-Gordan coefficients or 3J symbol, which define three-valent tensors. In general, we consider n-valent tensors, which appear in the problem of adding, for example, n-1 angular momenta, quantum angular momenta. As I mentioned, the kinematical Hilbert space in loop quantum gravity is spanned by the spin network states. On this space, quantum operators of geometry are defined, such as area operator or volume operator. Gravity is a fully constrained system, and in loop quantum gravity, the constraints become quantum operators, and we look for the states annihilated by the constraint operators. We say that they form a physical Hilbert space. Spin foams were constructed as histories of spin networks. As such, they have two-dimensional structure. A history of a node is an edge. A history of a link is a two-dimensional object, a face. This is a foam describing a history of this network into the other one. What will be the definition of a spin foam I will use today? It will be not an operator spin foam, but the standard one. A spin foam will be a triple, an oriented two-complex kappa with a boundary, with the coloring of its faces with irreducible representations of a group. I will assume it's compact for simplicity in this talk. The edges are labeled with tensors invariant under the action of the group. What's the idea of the relation between loop quantum gravity and the spin foam models is that the spin foam models define the physical scalar product between the spin network states. We want to think about this physical scalar product as an expression of this form, and we believe it can be expressed as a sum over spin foam amplitudes, where each spin foam amplitude takes this form. It is a product of vertex amplitudes, edge amplitudes, face amplitudes, and boundary length amplitudes. We further assume that each amplitude depends only on the local data. That means, for example, that the vertex amplitudes depends on a small neighborhood of the vertex. There has been some work in the direction of finding the relation, and we contributed to this development. And however, I believe the work is not done yet. First, I will talk about our work on finding the relation between the EPRL spin-foam model and loop quantum gravity. For those who do not know, the starting point for loop quantum gravity and also one could say spin foams is the Holst-Palatini action, where E is a tetrad and F is a curvature of a connection, and beta is the so-called Barbero inertia parameter. In the spin foam theory, one rather prefers a formulation of gravity as a BF theory with simplicity constraints, forcing the B field to be of this form. The result, Engle, Pereira, Rovelli, and Livine constructed a spin foam model by discretizing the theory, the constraint BF theory, and obtained the following model. I'll describe an Euclidean version for simplicity. This model can be constructed using what I'll call an EPRL map. EPRL map maps an SU2 invariant tensor into spin4 invariant tensor. Why spin4? Well, spin4 is a double cover of SO4 group. The representations of the spin4 are labeled with pairs of spins, J plus and J minus. One of the results of imposing the constraint is a relation between J plus and J minus. An EPRL map maps an SU2 invariant tensor into spin4 invariant tensor in the following way. First, this tensor is embedded in the representation space of the spin4 group. Then it is projected onto the subspace of invariant tensors. The image of the map will be called the space of EPRL intertwiners. In the original paper, the EPRL maps were defined for n equal to 4, only for 4 valent nodes. And we noticed that they can be generalized to arbitrary n, and this allowed us to generalize the model to a broader class of forms that describes histories of arbitrary spin networks. And the resulting model is the following. An EPRL spin form is the triple, as before, where the faces of a form are labeled with spin 4 representations, where J plus and J minus are constrained. Also, not all intertwiners are allowed. We restrict to the subspace of EPRL intertwiners. And the spin foam amplitude is a product of boundary link amplitudes, phase amplitudes, and vertex amplitudes, where the boundary link amplitudes and phase amplitudes are given by the dimension of the representation. And the vertex amplitude is given by appropriate contraction of a tensor product of intertwiners corresponding to edges meeting at the vertex V. And I should say, when we sum over the intertwiners, we will sum over orthonormal basis of the EPRL intertwiners. There were some further developments, even more than I wrote here, but I believe these are the most important for my today's talk. First of all, the model has been generalized to Laurentian version. Already in the original paper, a Laurentian version has been proposed, but also for the generalized model, the Laurentian version exists. However, the Lorentz group is non-compact and needs to be dealt with special care. Semi-classical limit has been studied of the original EPRL model, and as far as I understand, Simone will talk in his talk later about the semi-classical limit of a generalization EPRL model. The model suffers from the sum over spin divergences. You need to sum over possible labeling of the faces, and the sum is usually divergent and it needs to be regularized. The most elegant regularization is using quantum groups. The generalization soon after it was proposed raised the problem of what is the class of allowed forms, and we also work on this problem together with Jurek and with Jacek Puchta. Some restrictions on the so we considered quite general class, and some restrictions on this class have been considered recently, and I believe the derivation I'll present in the next part will tell us what's another possible class of forms, another restriction. The generalized model has been applied to cosmology and black hole physics, and the technical tool used in this application is a perturbative expansion in the number of internal vertices of the form. However, the justification comes from the derivation of a spin-form model from the canonical theory, and the EPRL model was derived by discretizing theory and quantizing covariantly. Therefore, I write here the justification is not clear. I believe it should be justified by a proper derivation of a spin-form model from the canonical theory. And this was at least my main motivation to derive such model. And in fact, we proposed a derivation of a model from a model of loop quantum gravity coupled to massless scalar field. So how to derive such spin-form model? The first ideas date back to the early works of Reisenberger and Rovelli, from the early works on the spin-form models. In this seminal paper, a derivation has been proposed. I believe it applies very well to an evolution operator. However, if it comes to the physical scalar product, it needs an averaging, group averaging, which involves integrals over infinite interval, and the integrals are over polynomial functions. So they lead to divergences, and so the interpretation was not clear to me. However, later on, there was an important work in the context of loop quantum cosmology in the symmetry reduced model by Ashtekar, Campilla, and Henderson, and where such derivation was proposed for the physical scalar product, for the one could say projector onto the physical Hilbert space. However, I think the model was not perfect because the amplitudes did not have the local form I told before. They were not a product of, say, vertex amplitudes times edge amplitudes times phase amplitudes are appropriate dimension lower. However, for the reduced theory. However, there was later work by Henderson, Rovelli, Vidotto, Wilson, Hewitt, where they introduced a regulator, and after introducing the regulator, the amplitude nicely splits into a product of amplitudes. So this is almost all you need to derive the theory. You need the next thing you need a model of loop quantum gravity from which you will start. So these are the main techniques we'll use, and the model will be the model about which Christina talked before in her earlier talk. And so how do you start? First you go skiing, and maybe that's not a necessary point, but this is how we started the project. And the results are the following. We took actually the version of the canonical theory proposed by Jurek, Mehdi, and Ilka. Actually, Ilka talked about this in the defense during the lunch break. In this approach of the Hilbert's, the space of solutions of the constraints looks in the following way. The solutions of the Gauss constraint are solved as usually by using spin network states. The diffeomorphism constraint is also solved as usually by averaging with respect to the action of the diffeomorphism group on the spin network states. And the scalar constraint is defined on the space of partial solutions to the vector constraints and of the solutions to the Gauss constraint, called the Vertex Hilbert space. The basis of this space is formed by states obtained from the spin network states by averaging over all diffeomorphisms that act trivially on the set of nodes of the graph. And the operator is a sum of a Laurentian part and Euclidean part, and there is a parameter in front of the Euclidean part which will serve the role of an expansion parameter in our approach. And you can think of this splitting as a splitting into the free part and interacting part. This splitting is not unique, however, we chose this particular splitting into free part and interacting part because it's, I believe, the closest to the spin foam approach. Why? First of all, the Laurentian part in the Warsaw proposal is easily diagonalizable in the spin network basis. It's because it does not change the graph nor the representation labels. It acts non-trivially in the intertwiner space. So the Laurentian part is completely determined by square matrices that can be defined by the angular momentum operators by the following expression. This expression is motivated by the Regge calculus in 3D. You can think of this as the dihedral angle and about this as the areas. The Euclidean part is more non-trivial. It creates or annihilates loops. The loops needs to be tangential to two different links of the graph, and the new loops are labeled with a fixed representation label. The Euclidean part is defined by rectangular matrices, which I denote by this symbol here. And they can be again defined using the angular momentum operators. Let me just explain how this operator acts on an invariant tensor. The indices of the operators JR and JS act on the appropriate indices of the intertwiner, and the indices of this operator in the spin L representation corresponding to the loop are left free. So the operator acts from one space of invariance into the other space of invariance, a bigger one. So this describes the quantization of the gravitational part. If it comes to matter part, we took the polymer quantization. The polymer Hilbert space is spanned by functionals of real-valued scalar field that are of the following form, and the scalar product is is such that the functionals are orthonormal in this scalar product. This delta here stands for Kronecker delta. The states are eigenstates of the momentum operator. The Hilbert space is a tensor product of the vertex Hilbert space and the matter Hilbert space, the Hilbert space on which the scalar constraint operator will act. It can be shown that when acting on diffeomorphism in variant states, the scalar constraint can be brought into this form. It's a difference of a scalar field momentum squared and the gravitational part of the constraint. Our physical scalar product will be given by this expression. P stands for the projections onto the eigenvectors of the momentum operator of the scalar field. dp stands for the projections onto the generalized eigenvalues of the gravitational part of the constraint. And delta imposes the constraint. Actually, for simplicity, we restricted to positive frequencies. However, you can apply our strategy to negative frequencies as well. And this eta tilde stands for an averaging with respect to the remaining diffeomorphisms that permute the nodes of the graph. Next, what we did is we expanded the physical scalar product in the power series of the parameter lambda. And each coefficient in this expansion can be written as a sum of spin form amplitudes and is defined in terms of sum over spin forms and the residual diffeomorphisms. In the order m, the coefficient is defined by spin form amplitudes with m internal vertices, and therefore this is the vertex expansion used in the applications of spin forms to cosmology or black hole physics. How our spin forms look like? The forms are histories of spin networks where the loops are either added or subtracted between the links. So the faces look either like rectangles or they look like cones, or possibly two cones glued together. The faces are labeled in the following way. The faces that look like rectangles are labeled with the same representations as the boundary links. The edges are labeled with triples. And SU2 invariant tensor, a scalar field momentum, and a number, a sign, plus or minus 1. We further assume that the intertwiners are eigenvectors of the matrices defining the Laurentian part of the scalar constraint. The scalar field momentum is conserved along the edges, as well as the sign S. The spin form amplitudes look as follows. The amplitudes assigned to the edges look like the propagators of a scalar field which gains a mass, so a massive scalar field, more or less. The vertex amplitude is defined in terms of matrix elements of the Euclidean part of the scalar constraint. And the spin form amplitude is a product of edge amplitudes and vertex amplitudes. So let me summarize. In our work with Jurek, we generalized the EPRL spin form model to all loop quantum gravity states, and this model has found applications, for example, in cosmology or black hole physics. And in this application, an approximation is used called a vertex expansion. And I believe the proper justification of this expansion should come from a derivation of a model, spin form model from loop quantum gravity. And this is what we did in our second work. We derived a model from spin form model from a model of loop quantum gravity coupled to massless scalar field. The model provides a perturbative expansion for the physical scalar product, so it justifies the vertex expansion. It has some nice properties. The coefficients of this expansion are finite order by order. The structure group is SU2, so there are no Laurentian divergences. The spins are fixed by the boundary data, so there is no sum over spin divergences. And the number of forms is under control. So given two boundary states, the number of forms is actually finite. However, we still don't know what are the convergence properties of this series, whether the series converge or not, if they are asymptotic. This needs some further research. And I'd like to mention also that this derivation does not close the debate about the relation between spin forms and loop quantum gravity, because we do not know how our model relates to other models, say, for example, Barrett-Crane, EPRL, FK, or Barrett and Oriti, or other models. I mean, first one would need to couple a massless scalar field to them, and then one could try to compare. I'd like to thank you for your attention, and one moment, please. And I'd like to thank also Jurek. Thank you, Jurek, for everything you taught me, for all the advices you gave me, and thank you for the all interesting discussions and for the nice skiing time. Happy birthday.
Thank you. We have quite some time for questions, so perhaps I start from you and then you.
So in the spinfold model that you derive, do you see any, is there any way to see that the terms that correspond to two complexes with higher numbers of vertices are contributing less to the sum? In other words, do you see any possible justification, evidence for justification of the way that we usually neglect higher order spinfolds?
Yeah. So this relates to the question. This relates to the question whether the series is convergent or divergent. If we believe that the amplitude we found is analytic in our expansion parameter lambda, then for at least for sufficiently small lambda, we can say that that the more terms you take, the better approximation you get. So in this sense, yes, of course, we do not know if it's convergent, what's the radius of convergence. So if, for example, beta equal to the usual, the Barbera immunity parameter around 1/4 is within the radius, or probably the series is asymptotic, so we can take a few orders at which the approximation improves. However, at higher orders, it starts to diverge. So yes, I believe this is, we kept quite close to the standard derivation in quantum field theory. So this is like in QFT or like in QED, for example, I believe.
Okay, Simone.
I missed how you define the momentum V of the scalar field. Can you comment? Can you say again? In the formula with the edge amplitude, you had this momentum.
Here.
Next slide. At least right, that p squared there. How is it defined?
Well, this is an eigenvalue of the momentum operator of the scalar field at the node corresponding to the edge. So the history of a node is just one edge. It's always one edge, because either you add or subtract loops. So you either have cons attached to this edge or removed, or you have some pierogi like attached to this.
Such operator depends on the metric too, and a priori might depend on non-compatible or non-commutative components of the metric, right? I'm just a little bit confused. This is supposed to represent boxes G nu, nu, d nu, d nu, right? And in this, and in here, the metric also is quantized.
So actually, yeah. So actually, the point, the tricky part here, is already at this point that this form applies when we act with this operator on the diffeomorphism invariant state. So, for example, the spatial, the gradient of the scalar field operator disappears. I mean, on the space of diff invariant states. So what is here is not p mu contracted, but it's actually just an eigenvalue of this operator pi appearing here.
Thank you.
Carlos.
Oh, it's good that you have that slide. It's a very nice talk. Thank you. I got confused about one point, but maybe I'm missing something crucial here. What is it that makes the finiteness of each coefficient of one amplitude? Is the fact that you don't have sort of internal bubbles over which the sum of a spin could go up? Is that?
If it comes to bubbles, the trick is that I add only the cones have fixed representation label. We do not sum over possible labeling with spins of the cones. They are fixed. They are fixed in the canonical theory.
They're fixed by the boundary states, by the initial final states.
Yes. So first of all, the spin L assigned to the cone is fixed for the model.
Okay, so you don't have internal edges. That's the case. Edges that go from vertex to vertex.
Let me. It's somehow difficult to switch the slide.
Yeah.
Yeah. So the point is that the spins assigned to the faces which look like rectangles are completely fixed by the boundary spins.
Right.
And the spins assigned to the cones are completely fixed by our model.
Right.
We choose them to be equal to L.
Right.
Where L is some spin, some integer or half integer.
Right. So there's no case in which the same. This is a generic thing. I mean, there's no case in which you have one closing cone and then opening.
Yes, you can.
And in between the spin. No, I see. I got it. Yeah, I got it. Yeah. Thank you. Thank you.
If you do this closed cone, then it still has the spin L. You do not sum over the spins.
Okay. Yeah. The last question.
So I have a question to the Bavarian Mirzi parameter, because when I looked at that, well, with the original spin form model and the original formulation of the Laurentian constraint, then in the canonical theory, the Bavarian Mirzi parameter is essentially just multiplying the Laurentian Hamiltonian, whereas in the spin form model, it's restricting the embedding of the representations. So as far as I understand, you don't have this issue because you're always having SE2 representations, right?
Yes.
But could you see a way, like, to generalize that, to see how those two roles play together in the original formulations, or with your description of the Laurentian part?
I don't see right now, because for seeing this, I should start from a different Hamiltonian, I believe. I should start, for example, with the Hamiltonian acting on not in SU2 spin networks, but say in the Euclidean theory, SO4 or spin 4 spin networks. And then maybe I could see something like this. Maybe Norbert can he investigated that models with other than SU2 groups. Maybe he knows something more.
No, but I completely agree with what you just said. That's how it should be done.
Okay, so since we seem to be in agreement, I think we can thank the speaker again. And